In this video, we're going to take another look at an example in Python using class-based structures. In this example, we will cover the topic of gradient descent on surfaces. So this is a way that we can approximate water flow or continual gradual descent across a surface towards some kind of local minima or the kind of edge minima as it might be. So what we're not going to simulate in this example is the actual kind of trailing off of a surface. We also won't necessarily consider kind of top and bottom necessarily of the surface. So those are additional rules that we would be able to add into our script, basically saying if the normal is facing down and we arrive at a local minima, then allow for our particles simulating our water flow to actually drip or drop off of the surface of our kind of base geometry. Also, we could add rules for kind of particle, like water particle cohesion, and that would look pretty similar to some of the agent-based behaviors that we did in the last video. So we're not going to cover those in this video, but just keep those in mind. And as we're kind of walking through this example, try and test yourself and really think, like, how could we build a cohesion property inside of this script? So as I'm going through, maybe you're actually augmenting this video with your own kind of pseudocode and then building up a kind of coding structure from that prior video that we went through and combined elements of this video to kind of really make this code your own. There's several applications for this, one being approximation of water flow on a surface, which can then inform erosion. It can also inform water pooling or water collection. So I mean, in the simplest case, we could think about landscape drainage and understanding how water flows on a landscape. We could also think in that same example about the consequence of soil erosion on that. We could also think about the surface of a roof to really understand where gutters are needed or where the problem spots on a roof might be, where water might pool, which can be an issue for kind of wear or algae growth on a surface, or also leaking. We could also use a script like this to be able to analyze more complex geometry in order to find particular areas or to adjust the surface to channel water into particular areas, which we could then use for rainwater collection. So this also has a kind of property that allows for sustainable actions to be taken as a kind of result of this type of understanding. So there's a lot of different applications. We're going to look at it as a kind of tracing or surface drawing that allows us to understand the geometry better. So think a kind of contour map, or even just the edge rendering inside of Rhino, the way that Rhino renders edges of a surface, help us to understand some of the kind of dimensionality of that surface. Well, another way is to take certain properties like these kind of local minima, run that water across the surface or run these particles across the surface, and then render to our eye where those kind of patterns flow. So it's just another way of articulating certain features or properties of geometry. So we'll take a look at it in that sense, but again, there's a wide range of applications for this type of algorithm. We can get started by opening up a clean Python script inside of Rhino, and you'll see I have two geometries here. These two geometries are going to be the base geometries that will run for tests. So if you have access to this base 3DM file, then go ahead and open that up, and you should see these two geometries on separate layers. And then you should also see a set of points on this one surface. So we don't have points on the second one, and I'll explain why in a moment. But if you're following along with the base files, then these two are accessible to you. If not, just make any surface and you should be able to run the script on it when we go through this process. Also, if you notice, the surface on the left here is just an example from the mathematical surfaces video covering loops and nested loops and kind of understanding the surface parameters there. So we can reuse that for two reasons, because it has complex kind of surface geometry and surface features, which are going to be interesting to map via this water flow script, but also it's something that we already kind of are understanding the structure of, so we'll be able to unpack that in a certain way to be used in this script. So to get started in our Python script, I'm going to make a multi-line comment, and we can just say gradient descent on surfaces water flow. So I'll just leave it like that for now. And for these early rule sets, I'm actually referencing a tutorial by Woo Jae Sung. So I'm going to just leave a comment for us, reference rule set and structure by Woo Jae Sung. So there's a great PDF available on gradient descent by Woo Jae Sung on their website. So feel free to take a look at that as well. You should be able to find it by just searching gradient descent and then Woo Jae Sung. It's really helpful for understanding some of the kind of steps behind this process. So what I'm going to do in this video is really kind of translate some of those basic logics, which are general logics present in gradient descent, into Python code using classes. What are the goals of this algorithm? Well, the goal is one primary goal, which is to simulate water flow on a given surface. How can we do this? We can do this in three parts. Part one, we define a point or points on a surface, extract the surface slope. So we need to know the slope, especially the downward slope at that particular point. Determine which direction to move. So that's all part one, is essentially correlating a given point with a point on the surface and then properties of that surface so that we know how to move or where to move. What is part two? Part two is to actually move the point based on surface slope. And then we need to update that point position. So that should feel familiar from the last video. This is going to be fairly similar to the mesh crawlers. We're doing it this time on a surface, but it's a pretty similar structure to the kind of understanding and logics of a mesh crawler. We're going to have less complex behavioral parameters for this script, but as I mentioned, we could combine these two videos and then develop a kind of hybridized script that allows for more particle-based interaction. So you're welcome to do that on your own. All of the pieces are going to be present after watching the last video on agents and this video on gradient descent, but I'll leave it up to you all to kind of conceptualize that and think through how you could add those together. So part three, what is part three? Well, we're going to give ourselves the option to set multiple random points on the surface or extracted from the surface to simulate random rainfall. So interacting not just through singular points kind of drawn out or declared on the surface, but by kind of simulating this like drop or deposition from above. Now, this doesn't just apply to water flow or rainfall, let's say, but it could also relate to any kind of deposition-based fabrication. So we're not simulating a kind of particle-based or spring system-based deposition like in FDM deposition or kind of plastic extrusion, clay extrusion, those types of things. We could do that with a somewhat similar structure to what we're going through now and combined with some elements of our agent-based programming. We're not going to be able to use this script directly to do that. However, it does have some overlaps. Like if we know the kind of direction of flow, then we could control certain deposition elements or generate toolpaths based on those flows and coordinate the material behavior with the kind of generated toolpath. So this is getting us thinking a little bit more on how these kind of escape the digital and become actually part of our physical fabrication as well. I'll come back at certain points as we build this script out to return to logics and kind of build up how we can really think through this and how we break these parts as described here up into consumable or understandable Python code. But for now, I'm going to just jump in and cover some of the pieces that should be now very familiar. So we're going to interface with objects in Rhino. What do we need? We need to import Rhino script syntax as rs. How do we bring objects into Python? We use rs.getObject. What do we need to bring in? We need to bring in our surface. So I'm leaving a message, select surface, rs.filter surface. Now we need to save this as a variable, which we can call surface. What else do we need here? Well, we need either a singular point or a list of points. Now that we're kind of familiar with the structure of classes, I'm going to just jump straight into points, and we'll just go ahead and build the structure assuming we have multiple points so that we can build that kind of robustness from the start. So I'm going to say points equals rs.getObjects, plural, and leave a message to select points. Now our filter, we need to filter point. Now with this started, to test we can click play, select our surface and then our points, hit enter, and we get no errors, so we're ready for the next step. I'll copy these lines, create a line break just for our kind of visuals so that we can understand that, and then comment out these lines above. And now we'll jump into the actual coding structure. So we're reading in our surface, we're reading in our points. Now, what is going to be the thing that we kind of take action on or move in our scene? Well, we don't want to move the surface, we want to maybe read some properties of the surface. Like our agent-based algorithm, we want to represent our agents with points in space and then move those points in space based on vector motion. So how can we do this? Well, we can construct a class here, which we'll call not agent, but we'll call this gradient descent. And we could even refer to this as gradient descent particle if we wanted to refer to it as one kind of particular element in the class name, so we understand it as, you know, an agent in a system of agents, which this is not behavioral agents, but, you know, some kind of particle within a system of particles. We could also just call this particle, I suppose, but for the sake of this entire set of course videos, I'm going to call it gradient descent so that we can kind of clarify to ourselves when we look at this code that we're covering the specifics of gradient descent. Because a particle could be very similarly structured to an agent-based particle, so I want to just say gradient descent for that clarification. Now, if we're passing something into any class, we need a constructor function, so init underscore underscore, and then self. Now we can just say pass for now, and then move down below our get objects. So we have our surface, we have our points. As I mentioned, the points are what we want to operate on. What do we want to do with those points? Like with the agents, we want to take those point values, feed them into our class to be able to perform some actions on them. How do we do that? Well, first thing we need to do is loop through for point in points. Now, inside of this loop, for each point, we want to construct an instance of the class that we just made. So an instance of the class by typing the name, opening parentheses, and closing parentheses. If we just say print, we would now get a printout of each of those instances. So hit play, select the surface and then the points, and we now have, I'm not sure how many points we actually have in the document, but it looks like around 10. I'm not sure if that's the exact right number. We also have 80 and it goes to 88. So, okay, so there's 9 total points here. So 9 unique instances. If we want to pass in some values, we need to ask ourselves what we need to pass in. Just like with the agents, we want to pass in our current position. So this point position in our list of points. How do we pass in a position? rs.point coordinates. What do we feed in? The GUID of our point. That gives us the X, Y, and Z value from this point GUID. Now I can remove this print statement because it would just continue to print those instances. And now we need to pass this into our constructor function. So next to self, we need to pass in underscore pause. And now where we have pass, we can actually set this to a property in our class, self.pause equals pause. Now print self.pause. Hit play, select our surface and then our points. And now we get our initial positions for each of these points in our point list. Now we can jump into the next step, copy, comment out, and paste. What is our next step? Well, like with our crawlers, we know that we have these particular points. They are located on the surface to start. We could even place them somewhere above or off the surface. But what we want to do in this particular script is snap them onto the surface and always run the points relative to a closest point on the surface, meaning we always want to be snapping our self.pause to a point on the surface. We could lift this point up, hit play, select our surface and then our points, and it's going to still consider that one of our points, which is at 12 units in the Z. So it's off the surface in the Z. So we want to snap that back down to values or closest values on our actual surface. Well, how can we do that? We can read in our surface as well. So feed in the surface that we've gotten. So comma surface, where we're instantiating our class. Now we need to pass that value in, underscore surface. And inside of this constructor, we can save self.surf as a property inside of our class. Now, do we want pause or do we want the closest point on our surface? We want the closest point on our surface. How do we get the closest point on our surface? rs.surface closest point. What does this take as inputs? A surface ID and a test point. So we can feed in here a surface ID, self.surface, and our test point underscore pause. What does it output? It outputs a list with 2 numbers, a U and a V. So these are actually the parameters on our surface and not a point. This is super critical. This gives us a parameter set and not a point. So it gives us a U value and a V value that identifies the closest point parameter on that surface. It is not a point. To convert it to a point, we need to use a function called rs.evaluate surface. What does evaluate surface do? It reads in a surface, self.surface, and then a U and V value. We have those in our point parameters. And then what this is going to do is translate those UV values into an actual point. So we can say param of 0, param of 1. Another way of doing this is just saying, instead of param at all, we can say U comma V. And then here where we run evaluate, we can say U comma V. And then that's going to actually make the point that is closest to our particular point that we've selected. I can now paste this and override underscore pause there. And we now have self.pause equal to the closest point on the surface from the very start. Now, if we were to use rs.addPoint to visualize that, we would just see duplicated points being placed on our surface. We can hit play, select our surface, and then select our points just to make sure that we are still getting printouts. They should be the exact same values since these points exist on the surface. But just to make sure we're not getting errors. So we're not getting errors. So we can go ahead and copy all of this, comment it out, and step into the next step. What is our next step? Our next step is to actually perform an action on these points. How do we perform an action? Well, we're going to structure a move function, feed in self. What are we going to do inside of our move function? We are going to create an updated point position, so override that self.pos. How do we override it? With a self.vec, with a vector that allows us to perform a move action. So we could say equals self.pos plus self.vec. We don't have a property self.vec, so we need to make that in our constructor, but we can also shorten this down already by just saying plus equals self.vec. Those are the exact same, if you remember, so we'll just shorten that down. Now we need to make this a property in our constructor. What is our self.vec? Well, to start with, we want it to be just an empty vector or a zero vector. So rs.createVector, feed in an x, y, and z value, so 0, 0, 0, close parentheses. That gives us a starting vector of just 0. So when we now run this again, it wouldn't move the point at all, but we would be applying that 0 length vector to our position, updating our position. And then, in case this vector is somewhere off of the surface of our surface, we need to again run this closest point and evaluate. This time we're not feeding in underscore pos, we're feeding in self.pos. So we're updating that position and then snapping it back and updating the position again. So we're always updating first based on a vector motion and then based on the closest point on the surface to always be snapping it back to our surface. How do we run this function? We run this function by saving out our instance as a particular name, so my GD for gradient descent, calling that particular instance, and then its method move, open and close parentheses. It doesn't have any inputs, just self, which automatically is given into the function. So we don't need to give any inputs when we call it. So now if we make a print statement for self.pos, we can just make sure that this is all working, hit play, select our surface, and then our points. And we get those printouts. Now, these points should not have changed in value. Why should they have not changed in value? Even though we're doing a whole lot of stuff, the points exist on the surface, so when they snap for the first time, it's the same value. Our vector value is 0, so when we update that, it's the same value. Since the point has not moved when we've updated it, it's snapping to the surface while it's already on the surface, so it's the same value. So there's now at least 3 different times, 4 if you include the initial position, that the point has not changed in value. But this is the structure to allow us to change this in value. So we can now copy and comment this out, and step into the next step. What is our next step here? Our next step is to actually change this vector. By updating this vector, we're going to be able to read in some data or give some information, create a vector, which is that movement or motion vector, and now our point will actually move along our surface. So we have the structure set up, but there's no motion yet. To get that motion, we need another function, which we're going to call def getVec. We don't need any inputs into this function yet, and we might not at all actually. So right now we're just going to feed in self, and we can just type pass. Now where do we want to call this getVec? We want to call it every time we go to move. Why is this? Because we have a self.vec that needs updating every time we run this. Well, if the self.vec is what we need to update, then we need to call this before self.vec is used in this move function. So there's only one location we can place that, which is inside the move function and above our self.pos plus equals self.vec. So here we know that we want to manipulate self.vec. So self.vec set that equal to, and then we're going to say the return of this function, so self.getVec. If we're returning a value and overriding our self.vec, that means inside of this function, we need to return some value, which we'll call vec. We're not returning self.vec because we actually want to use this as a local variable inside of this function, not the property in the class self.vec, just vec. Okay, so now what do we need inside of this function? We need to start setting up those rules to calculate or extract the properties of the surface to move or create that motion vector based on the slope of the surface. So how do we do this? I'm going to minimize this script and zoom in Rhino, and we can take a look at what this structure is going to be. So if we look at this surface, as we move across this edge, you see that the slope is increasingly downward. So it's rotating increasingly downward. Now, to get that curvature or to get that slope of our surface, what we have to do first is find that closest point. So snap our point, let's say we're evaluating this point, snap that point to the surface. And now, once we find the closest point on our surface, what do we get as an output there? Well, we get our parameters on our surface, which we can then convert to an actual point. What else can we get from a surface? We can get the normal, which is perpendicular to the surface at that point. So if we just draw, right now I'll draw a vertical vector, and maybe we can rotate this slightly because it looks like it's slightly tilted. So we'll do that rotation. And let's say that this is the approximation, at least, for that particular normal. So what is a normal? It is the perpendicular vector to a given face. Now, we can get that, again, by finding that closest point parameter, or closest parameter on the surface, using that parameter to get that normal. So if we have a normal like that, do we want the normal? No, the normal is just perpendicular to the surface. What do we actually want? We want some vector that approximates the actual slope. So the slope in this case is some vector like that. We can see that as this surface spirals down, there's a local valley here. So we would want this particular point to go into the valley and then be flowing down this channel. So we have this kind of vortexing or spiraling, so we should see our points being affected by that spiraling, responding to those local slopes. Well, what do we know about vector math that allows us to get some vector that would give us this slope value? One thing that we could do is draw a vector in the z-axis. So from this point, exactly in the z-axis. So we have two vectors now. We have our normal vector, and then we have our z-axis vector. Between these two vectors exists a plane. What we want in the end to be able to use for our movement vector is going to be the vector that is 90 degrees or at a right angle to this normal vector, since we know that the normal vector is perpendicular to the slope of that surface. So we want a 90-degree vector relative to this normal vector, and we want that one that's facing down. So we know that we want that to be 90 degrees. Which plane does that occur on? Well, it's going to occur on the same plane as the difference between this vector and the z vector. So between these, a plane can be drawn out. So we'll do 3 point, and I'll draw out a plane here. So now the question is, what types of operations do we know that we can do with vectors in order to be able to extract that? So we have some relationship here that all three of these exist on some plane. we can draw some relationship between the z-axis then and our current normal in order to maybe get the slope that we're looking for here. Well, what do we know about vectors? One of the things that we know is that the cross product of two vectors with the right-hand rule, so the cross product of vector A times vector B gives us a resultant vector that is at 90 degrees to both of them. So in this example, if vector A is our index finger with our right hand, and then vector B is our middle finger in this example, then our thumb, which is pointing up, is going to be the cross product resultant. If we flip those vectors, then our thumb is now pointing down, and we would get a downward facing vector. So if we take a look at these two vectors, and we were to use the z-axis as our A vector and our normal as our B vector, then we would get a vector pointing perpendicular to both of those vectors somewhere here. So that would be where our thumb is pointing, perpendicular to both of those vectors. It would also be perpendicular to the plane that is drawn between them. So how can we get that adjusted to give us that slope value? Well, we can just rotate that 90 degrees using the axis of our normal. So take that resultant value from the cross product and rotate it around the normal. And now our thumb is pointing down. So now our thumb is pointing down that slope. And I can prove this here with a series of geometric operations that approximate what our cross product is doing. So if we have these two vectors here, I'm going to start by representing the result with an average. So this is going to give us an idea of that resultant vector. So I'm going to draw this out and then scale. So this is addition and then division, vector addition and then vector addition gives us the resultant averaged vector. Now what do we want to do for this example with this vector? We want to rotate 3D along this plane, but actually 90 degrees to that plane. How do we rotate 90 degrees to that plane? Well, we can draw the axis from one of these vectors to the perpendicular point on the other vector. So perpendicular point here on the other vector. And now click on the base point and type 90. Now we can move this. So move this so that it's seated or starting at the same starting point as our other two vectors. So we now get one here. Now if I rotate 3D again, because we don't want that vector sticking out, right? It's pointing up. We want the vector pointing down on this slope. So if we use our normal vector here, which is the second vector, use that as the axis, then we can click on our vector, type 90, and rotate it 90. We now get a resultant vector that is exactly pointing down our slope. So that's the kind of geometric proof that kind of combines with the mathematic proof that the cross product of two vectors, especially the cross product of any vector relative to the z, rotated 90 degrees, gives us this particular perpendicular slope of this surface. Okay, so now we can jump back into the code and we can build up that definition inside of our getVec function. So what do we need first? We again need to measure the closest point at this particular time because we're doing it after, but we need to do it before. So we need to measure the closest point when we call this function. How can we do that? Well, we can say, this time we'll just say param equals rs.surface closest point, like we did previously, given self.surf and self.pos, our current position, whatever that is. Now what do we need? We need two vectors. We need our normal vector, which we can say is vec1, and we need our vec2, which is going to be our z-axis vector. We can just make our z-axis vector 0, 0, 1. How do we get our normal? rs.surface normal. What does this take in? Self.surf, so a surface ID. What else? UV parameter. So a list or a tuple of U and V values. So we can just feed in our param as a whole. So we don't need to split them as U and V's in surface normal, but in evaluate surface, we do need to feed in each of those values as separate inputs to that function. So that's why it's allowed to be param here and not UV, whereas up at the top, we have to split it into U and V. Now, do we want the vec1 and 2? No, we want the cross product first. So we'll do cross product of vec1 comma vec2. Now we're already returning that vec value. And to visualize this, we can just go ahead and in our move function, add the updated point after we're snapping it back to the surface. So we're calling this function. It's drawing out the two vectors, first the normal, getting the normal, and then relating that to our z-axis. I did the geometric proof for the cross product, which gives us that perpendicular vector. If we rotate that 90 degrees, counterclockwise rotation, so 90-degree rotation gives us that slope pointing down. So then we're returning that, we're storing that as self.vec, we're adding that and updating our self.pos, we're snapping it back to the surface, and we are adding that point to our document. So now if I click play, select our surface and then our points, we now get points drawn out. So we can see a few of those points drawn out and added to our document that are that cross product output, and then being snapped back on to our surface. Now, if we take a look again at that, we'll notice that those are often exactly perpendicular, or at least visually appear perpendicular, but we know that they're exactly perpendicular to the slope vector. So they're not actually being drawn at the slope vector that we want. Like in this example, the slope vector is very clearly just straight down pretty much following this edge, and we're drawing that point over here. So at 90 degrees, how do we change that? We already said this in that proof that we want to rotate this vector. We can rotate this with vector rotate, rs.vector rotate, and we can rotate this 90 degrees. So what does vector rotate take in? A vector, which is vec, a degree, so 90. If we use, so there's two right-hand rules. We have vector right-hand rule, which is the cross product rule, A, B, and then equals your thumb. So index plus times the middle finger equals your thumb, right? So that's kind of the three-axis rule, x, y, x times y is z. So we can understand that using our right-hand rule. The second right-hand rule is the curl of your fingers relative to an axis that is your thumb gives you the rotation. So an up axis rotated 90 degrees is counterclockwise. So we have 90 degrees, which gives us that counterclockwise rotation around which axis? Our normal. What is our normal? Vec1. Now if we click play, select our surface and then our points, we now get all of our points, our second points here, being drawn below our current ones. So they're all now being drawn at a lower point. You can see the slope is there. It's being drawn at that decreasing slope. So we have that updated position. Now, like in previous examples, if we want to run this multiple times, we could just use a loop to do it and run the move function multiple times. But in this case, we have a specific condition that we want our function to stop at. What is that condition? Well, if our second point equals our current point, if our updated point position equals our current position, that means that we're somewhere down here at the lowest possible value And that means our particles can't move any lower, so they would just continue on forever staying there. So we have a condition that says when it gets to that lowest point, just stop. And now this is where if you wanted to say if it gets to that position, then drip down and allow it to continue dripping until it hits another surface, you could do that as well. But also if we have a surface, like let's say this wasn't a spiral, and we had a local minima that pools, and there is nowhere for that particle to go any further down than where it is, then we just want it to stop. Well, if we know that our movement is related to a specific condition, then it probably makes sense not to loop for a given number of iterations or number of steps, but instead to check for that condition. What is that condition? If self.pos, our updated position, and not our position, but just our z value, is less than our previous position, which we can call prevpos.z. So if our updated position is z value is less than our previous position z value, then call the move function again, because then we can keep moving. What do we need to do next? We need to set our prevpos. So prevpos equals self.pos. Store that as a temporary value before we do all of the updating here. So now we can make that comparison. Another thing we can do is we can check, so after we've updated, if that is less than the previous position. So if we're continuing to move down and we're able to move down, then call the move again. Now, another thing that we can check, if we wanted to give a tolerance for this, so if it's less than, fine, but that might let it run on when really it's just kind of moving back and forth a very small increment. So how would we change this to allow for a kind of tolerance? Well, we could say also if the absolute value signified by ABS and then open parentheses, so absolute value self.pos.z minus prevpos.z. So the difference between those as a positive integer, so absolute value giving us only that positive integer, the magnitude of that value. Only run the move function if this is greater than 0.1. So if it's a smaller value than 0.1 and the difference is so minute that we won't even register it, that's just going to take forever to compute, and it's going to waste our time. So we don't want to waste our time. So now we can add that add point, our updated position, and call our move function again, self.move. So we're giving ourselves a conditional here if it's a less than, and then also a conditional if the difference magnitude is greater than a certain tolerance value. Now, we could combine these and add them together. We could also say if it's less than and the absolute value, so we could just join these here and say if it's less than and that magnitude is greater than, then run. You can do it either way, nesting both conditions or running the and. Totally up to you. But there's also other ways that we can give a kind of tolerance, but this is just one particular way. So now if we run this, this is going to run until that condition is met. So if I click play, select our surface, and then our points, hit enter, select last, we now see our points running, and then they get to the bottom, and they continue moving until they eventually stop and stop moving more than 0.01. So then they stop. And we're just rendering them right now as points. And you can see that they're moving down relative to the surface slope. So it runs along this side here. And then as we get to the bottom, we see that it's just running very slowly along that bottom edge. So it's kind of pooling along that bottom edge, which is the local minima. Now we can undo that, and we can copy and paste this and move to the next step. Comment this out and move to the next step. What is our next step? Well, we probably don't want it deposited as points for the same reason we didn't want our agents to be deposited as points. Instead, what we might want is to add a render function to render this as trails. And we're going to be doing this at the exact same way that we did it inside of our agents. So we're going to add a render function, feed in self. How do we render trails? By adding either a polyline. So we can just say add polyline. What do we need here? Well, we need a list of, so self dot, and then some list property. So we can say trail points that are all of the stored history points from this gradient descent. So from each one of the original points, we want to store all of their updated positions. So we need to go to our constructor, make that as an empty list, and we need to start by appending our original value. So append self.pos. Why do we append self.pos at the start? Because we're then going to also append, instead of adding here. So that's going to append every time it's updated, but to get the very first one, we need it in the constructor function as well. So now we have those lists being stored. Now, when do we want to call the render? Well, if we called it every single time we did the move, then we would be making a new curve every single time we run it, which we don't want to do that. We just want to call it after we've run all of the moves. How do we do that? We call mygd.render after the move function. So this is going to loop through each point in our list of points, construct the particle for gradient descent, run the move. Inside of the move, we actually call it recursively. So it's going to finish this entire operation. And then once it finishes updating all of the moves for that particular point, it's going to render that trail and then move on to the next one. So now we could click play, select our surface and then our points. So we're getting an error here. And this error is because we don't have a check of the length of our trail point. So we're appending as we update, but what if our point actually started at a local minima and it doesn't have anywhere to go? So before we render this polyline, we need to double check that our trail points are long enough, at least 2 points. So if length self.trailPoints is greater than 2, it needs to be at least 2 points. So we'll just say greater than 2, so 3 points. And if it is, then let's make that polyline. So now we can click play, select our surface and our points. Now we can select all of these curves, and we now have those polylines drawn out. These polylines are drawn at the particular resolution of the unit size that we're creating in our move vector. How do we control that? Well, we can control that like with the agents by creating a maximum velocity for these to move with. So I'm going to copy this all the way down, comment it out, and we'll step into what is basically the last step for our actual motion setup, and then we'll take a look at producing random rainfall. So how do we control the vector value? We control the vector value where we're returning it here. So the first thing we might want to do is ensure that this is a vector with length 1. How do we do that? We unitize it. So this just takes that vector and basically scales it to a length of 1. Now what can we do? Now that we know that this is a length of 1 and consistent every single time, we can scale it by a parameter maxVal. Now we can save or declare this parameter up at the top. And if we change this to 0.2, what were those large kind of low resolution segments of our polyline are going to get a lot finer with a value of 0.2, because that vector value is going to be limited to a length of 0.2. So we'll get much finer motion along the surface of our surface. So if I hit play now, select that surface, select our points, we now can see that that's a much finer resolution motion being picked up along our surface. So we're getting even the kind of folds or like kinks in the surface are being rendered into our trail curves. And we can see that because that's a finer degree of step, we're also making those checks or test values more time. So we're responding to more of these kind of local features of the surface. So you're seeing that one just runs along the edge, and these two run along this kind of ridged valley. And then this one on the outside briefly steps over this ridged valley, but as it kind of flips or inverts, it then runs along the side until it hits this local minima of this kind of inverted ridge. And these 2 points must be already at a local minima. So there must just be a little dip there, so they're actually not creating any points. So that's just something to note. When we look at the kind of random rainfall, we'll get a better picture of how these kind of surfaces actually behave without just these few points being drawn out. As we render more points and more trails along the surface, it gives us a better picture of how these kind of surfaces act. When we run this right now, since our render function exists inside of our loop, we're going to be rendering out those trails each separately. So we're going to do one full point trail, then the next full point trail, then the next, then the next. And this is a very slow operation to visualize. To speed this up, we can just turn off our redraw. So set redraw equal to false. And then after we run through the entire loop, set it equal to true. Now hit play, select our surface and then our points. So now it just thinks for a moment, draws out all of our curves and simultaneously displays them. So we see 4 of these curves being drawn out. These other ones must be at local minima, so they're not making any curves for us to draw out. Okay, so then what's the next step? The next step is going to be to make or produce our random rainfall. So instead of giving an input of these points that we've drawn out in space by just placing points on our surface, which happen to be at the edges because it's hard to place points on surfaces on the actual surface. So what are we going to do? We're going to replace this input of our list of points we've gotten from the document with a generated set of points. How can we do this? We can do this kind of like actually the way that we've constructed this mathematical surface by using the surface domains and then divisions on the surface domain. Now we're not going to be kind of generating, a form, so we're not using mathematical functions. I guess we're using very basic operations in math, but not trigonometric functions. But we are going to use the kind of concept of the u and v parameters of the surface to be able to generate a set of random points that in particular will be facing up, because we want to get just the kind of points facing up as though the rainfall is hitting it, and we'll have a kind of random value to only keep certain ones of those. If we kept all of them at a certain density, it would be far too much. So we want to just keep a few to produce the kind of randomness of rainfall. Okay, so how are we going to do that? We're going to replace this points list. How do we replace that points list? Well, we can start by developing a set of points on the surface. One way of doing this is dividing the surface using its domain. So this is similar to if we go all the way back to our intros to Grasshopper, where we created surface divisions to operate on a surface. So we use the u and v parameters to operate through surface divisions to then create, these kind of panelization methods. Well, we're not creating panelization methods, but this will allow us to essentially extract kind of strips of points on the surface at a given density. How do we do this? To start, we can use the command surface domain. What does this take in? It takes in a surface. What else does it take in? A direction, where 0 is u and 1 is v. So we need one of each. We need the u and the v's. What does this output? A domain of a surface object in the specified direction. What is a domain? It's a list of 2 number values. So this is a minimum and a maximum that create that domain. So a domain is a minimum to a maximum. So we can unpack this as umin, comma, umax, and set that equal to the output of surface with an input of both surface and 0 to get those u values. Now if we copy and paste this down, to get the v's, we just need an input of 1, as it says here in our help function. And now we need to say vmin and vmax. What do we want to do with these? Well, we know that we want to add points, so generate points, and add them into this list points that we already had. What can we do with our surface domain to get points on the surface? Well, we can define a set of divisions. So let's put this above our surface get object, or actually maybe we'll just do right below, and we'll call this divisions in all caps, and we can just start with a value of 10. What do we do with our divisions? We loop through for u in range divisions, for v in range divisions. Now this should look pretty similar to our mathematical loops that generated this surface. Right, we're using a nested loop with u and v values. What did we have to do in that video to create this? We had to adapt the u and v values, which right now are looping through the number of divisions. We had to convert those, in that example, into inputs of radians for our trigonometric functions. Now we don't have to do that here. What do we have to do though? We have to adapt these u values, which will range from 0 to 9, 10 divisions, but we have a u and a max value that doesn't necessarily range from 0 to 9. So let's go ahead and also just print out umin, comma u max, print v min, comma v max. And then I'm going to comment out these lines for now, and then we'll come back to them. And then I'll say pass, pass. So we're just printing out the umin, umax, vmin, vmax. Click play, select our surface. What do we get? 0 to 5.487 and 0 to 12.289. We would never guess those values. So they're particular to each surface. We would never guess them. So how can we use those values? Because we need these divisions to be not just 0 to 9, but we need 10 segments of the 0 to 5.48 in the U. How do we do that? How do we create segments or partial kind of domains or clippings of one given domain? Well, we can start by taking the entire length of that domain, or the kind of range of that domain, meaning we'll take that 5.48 value minus 0, and that gives us how long the entire thing is. Then what do we do with that? Well, if we divide it by the number of total divisions, so divided by 10, that gives us the stepping value. So every time we want to create a new U, we want to take U and multiply it by that stepping value, which is that 5.48 minus 0 divided by 10 times whatever our U value is, which is 0, 1, 2, 3, all the way to 9. That gives us increments in the U that separates this domain into 10 divisions. So what is our U equal to? Our U is equal to U times U max minus U min divided by divisions. What is our V equal to? V equals V times V max minus V min divided by divisions. So this gives us the incremental steps, and we can print each one. So print U, print V through each of these divisions. So it gives us basically chunks of parameters that separate our total domains for the surface. So if we hit play, select our surface, first it gives us the total domains, and we can see the U and V values to start are 0, 0, and then 1.2, 2.4, 3.6 comma 4.9, and actually, sorry, that's not quite true. So it goes 0 comma 0, which is the U first, and then it steps through all of the V's. So it's going to go 0 comma 0, then 0 comma 1.22, then 0 comma 2.4, 0 comma 3.6, and so on. So if we print U comma V instead of printing U there, we'll see that printout. So hit play, select our surface, and now we see 0 comma 0, 0 comma 1.2, 0 comma 2.4, 0 comma 3.6, 0 comma 4.9. So we see that incrementing through our U and V values. Now, how do we do something with these? Well, like we did using our surface closest point and evaluate surface, we could just make a point using rs.evaluate surface. What does this take in? It takes in our surface, which we have received by the get object. What else does it take in? It takes in a parameter. What are our parameters? Our parameters are U comma V. So we're looping through all of those parameters. What do we want to do with this at first? We want to just visualize this to make sure we're doing the right thing by adding this to our document. So add point. Let's add that point that we've just evaluated to our document to make sure that this is working. Play, select our surface. Now we're adding all of those strips of points to our document. If we increase this density, hit play, select our surface, we'll get a higher density of those U and V strips. So we're seeing many more points added to our document there in the U and V strip values. We can also see that we have, I think, many more in the, we can double check this, but it must be in the, it's in this axis, which was iterating through first. So I think we have more in the V, so we might want more divisions in the V. So we might say divisions times 2, and then we might divide by divisions times 2, so that we get more divisions in the V axis. So if we hit play, select, we should see a more even distribution with more square cells being drawn out, which we do see. So those are more square cells being drawn out there. Okay. So now, in order to complete this as kind of rainfall and not just draw points, first, we don't want to make the points in our document. We want to append them to this list. So we want to say points.append. Okay, so we're appending that point output to our list of points. Now, when do we want to do this? Well, we only want to do this when the surface is facing up to catch the rain. How do we tell when a surface is facing up? We get the normal. What is the normal? And what values does it take? Well, it is the vector perpendicular to the surface. It takes in a surface ID, which we can say is surface. What else does it take in? It takes in a list or tuple of U and V values, which we can pass in, or a parameter of U and V values, which we have to nest inside of parentheses as an input to our surface normals. Now, it has to be not in parentheses for evaluate surface. It has to be in parentheses for surface normals. What do we want to do here? We want to check the angle between our normal and the z-axis facing up. And we want it to be within a certain degree to know that the surface is facing up in that particular location. So we need a vector, which is our z vector. So vec z equals rs dot create vector 0, 0, 1. Then we need to find an angle, which is the vector angle between these two vectors, so our normal and then our vector z. And then we can say if that angle is less than 15 degrees, then append points. So if we just comment out this append and then copy and paste this line to where we're adding the point, so that just so we can visualize that again. So we have this adding and visualizing. So if we hit play, then we should only see the surface normals that are facing up being stored as these points. So if we hit play, select our surface, we should see none of those points that are facing down on the surface being stored. And we are seeing that. Now, if we increase this value threshold for that angle, we should see more points being stored, but they should still be generally facing up, which we can see. So now we're getting almost all of the points that are visible from above, but none of the points that are visible from below. That's exactly what we want, as those are representative of rainfall. So we're getting exactly what we want there. So I'm going to just uncomment that out and delete our add point. And one last thing that we want to do here is add the randomization. What randomization? We want randbool, so random boolean, equals random.randint. What do we want to feed in here? Either a 0 or 1 value, so 0, 1, and it will choose either a random value of 0 or a random value of 1 for every single parameter on this particular surface. And actually, we can nest this inside and say only run that rand int inside of here if the angle is less than 45, and then we can say if randbool, so if it is a value of 1, then append it to our list. If we wanted to check that and that we're getting random values, we can again just go ahead and visualize by adding it to our document. Hit play, select our surface, and it's giving us an error that random is not defined because we need to import that random library. So import random. Now hit play, select our surface. Now it's those same points that we saw at the beginning, but randomly removed. And actually, if we hit play again, we're going to see new points being added. So if we hit play again, new random points will be added. So we're seeing additional points. So this is actually like, duration of rainfall now. So every time we run this, it's basically like a cloud depositing new rain particles. So what I want to do is now uncomment this, and we can append instead of adding these points to our document. But if we want to take a look at what I just described, which is actually iterating through multiple times, so not just each of the points, but actually each random depositions on our surface, we can do that as well, and we'll kind of look at what that is right after we make this running again as a whole with our trails running across our surface. So the first thing we need to do is just uncomment this. We have our points being appended. We can just remove the print statement for our umin and umax and vmin and vmax. And now, since we're not adding to the document, that should run faster. We're disabling redraw, and then we're moving and rendering. Now if we click play, we should be able to see the trails being drawn on our surface. So click play, select our surface. And now we are getting one issue here because we do need to adapt this actually for feeding in our point values. Why is this? Because we get an output of an X, Y, and Z value from our surface, and we're appending those, not a GUID, to our points list. That's actually great because we can just delete our point coordinates, and we can just directly feed in for point, which is an X, Y, and Z point, in points, feed that in. So we don't even need the point coordinates anymore. Now if we click play, select our surface, we wait a moment, and then our trails will be drawn out on our surface. So now we see all of those trails being drawn across our surface. And we can see where flow starts to happen over these edges. So it's even giving us a kind of understanding there of where a kind of gutter system is needed, or maybe a reveal that might need to be placed in this surface in order for rain to just not drip down the surface. We could also develop a texture that is actually simulating the wear on the surface or the weathering on the surface based on this rain flow. So if we know that rain is more likely to kind of pool in this valley and then drip down at this particular point, we would be able to pre-weather the texture for a visualization to be able to approximate the weathering that would occur on the surface. So if this was made out of metal, we could show that weathering in a texture using this simulation. You can see where all of these points are randomly distributed, and if we were to run it again, then we would get a totally different random set of points that would run in a similar pattern on this surface. One other thing that we can do in the script, besides running for multiple iterations, so kind of keeping an extended duration, let's say of rainfall, is we can make this tolerance a variable. So right now it's 0.01, but we've decreased our maximum velocity to 0.2. So it's still probably running for quite some time. So 0.01, we might want this value just divided by 10, let's say, so 0.02. Because as we decrease our max vel, the likelihood of this tolerance being met basically decreases. So we want this as a factor of max vel, and we can just call this max vel divided by 10. And if we wanted to adjust that to run it quicker, then we could do so as well. So I'll make that a factor of our max vel. And now we can try and run this on our second surface as well. So if I click play, select our surface, then we can wait for it to run, and we should see some trails generating onto this surface. So it will have its own particular surface characters and pooling behaviors, and you can see that they all pool at this particular location, or a lot of them pool at that particular location. We also have a kind of second saddle over here, so we have a little bit of runoff along this edge. So this is great for approximating kind of flow along a roof. For this particular one, on this one, it's great for maybe kind of understanding the feature properties or geometric properties of that particular geometry. If we hide the surface as well, we can still see the kind of approximation of that surface using just those gradient descent lines. And you can see where it's pooling at that one particular location on the surface. If we wanted to run this for multiple times, something that we could possibly do is add a color to our render function. And we could say the earlier the lighter and the later the darker, and that could visualize where things are happening. And we could make this kind of step in the blue color value. So I'm going to select all of this, and we can copy it into another step so that we don't mess up any of this bit. Comment that out and paste. Now what we want to do if we want to do this is not compute all of these all over again. So we would maybe want to store the U and V values, maybe even the normals and vectors. So store them all in a list because those are all going to be the same values, and then only run the conditional by iterating through that list again. Now, if we think that it's quick enough to just run this multiple times, then that's nice and easy, and we could just do that. But I think it's going to take a little bit of time to compute those. So we might want to save all of those into a list, and then strip out this conditional and run it in its own loop. So we could say params equal an empty list. Then we could say normals equal an empty list. And then our vector z is always going to be our vector z. But then we can store angles equal. And actually, we only need the angle here, so we don't even need our normals. And in fact, we don't even need our parameters. We do need our parameters, so we need params because we're using it in our evaluate surface. So we do need that. And that's it. We just need our angles and our parameters. So if we make these both empty lists, we can just say params.append. What are we appending? We're appending u, v. And then angles.append. What are we appending? We're appending angle. We can just keep those as flat lists and say for param in params. Or maybe we should say for angle in angles. And then we need for I angle in enumerate angles so that we can get those index values as well saved out. That way we can use those index values for our parameters u and v. So we'll say u comma v equals params of I of 0 comma params of I of 1. So unpacking those values we stored in the params list into our u and v values. And in fact, we can even do this nested inside of the conditional, so we only run it. And even further, we can do this inside of our rand bool to only run it there. So then if rand bool, so we're testing our angle from our angles list. We're generating a random value and evaluating the surface, and then we're using that list. We can now move this points list down here just in front of where we're actually appending to it. And if we want to run through each of these multiple times, so for kind of multiple rainfalls, we could make a variable called rainfall or duration. Maybe it's duration is better. So duration, time of rainfall. Duration equals, let's just start with 2 as a test. And then we can say for time in duration. And now we can't use just that number value because there's only one value there. It's not a list that we can iterate through. So we need to say for range duration, so range 2, which will be 0 and 1, 2 times, and then we just tab all of that in. Now every time we're generating a new list and we're generating new points, we're feeding those points in and creating new trails and adding those to our document. Now we need to do one additional step, and this additional step is going to be to render these a particular color. How can we render these a color? Well, we could use our time value here. So for time in range duration, which is 0 and 1 currently, we could pass this into our gradient descent. So we could say pass in time. We could read that into our class as a value time. We could then store that as self.time equals underscore time. So we're adding that into our constructor so that we can read in that time value as we loop through. So the first time step, time will be 0. So what if for the first time we want it to be entirely blue, and then more recent ones we want to be less blue? We can do that by adding a color to this object. So we can add rs.objectColor. What does this take in? Object IDs and then a color. So what color do we want? We want a color that equals blue. And we can set this equal to rs.createColor. What does this take in? It takes in an RGB value. Well, our RGB value will be 0. So R is red, 0, green, 0, blue, 255. That creates blue. If instead we wanted not just always to make our lines blue, but we want, let's say we want that color to change with our time value, what we could do is we could say 255 divided by duration times self.time. So as our time gets higher and we get closer to that end value of duration, we get a more blue, less black, more blue curve. We'll start out with an entirely black set of trails, and then eventually they will become more blue. So now object color takes in our object IDs, so we can just feed in rs.add polyline, and then a color, which we can use as our blue color. And then if we're going to use duration as a global variable, we may want to declare that at the top, so duration equals 2. Now we can click play, select our surface, and we'll now have to wait twice as it iterates through and renders first the first set of trails and then the second set of trails. And we should see that color change between them. So one should be black and one should be blue. So it's very subtle here. We can barely tell in the visualization. So to make this a little bit more visible, instead of keeping our essentially yellow constant and then changing our blue, we can actually set our incrementing, which we were using for the blue, as R and G, so that they range from 0 to 255, and then always keep our blue channel at 255. So this should give us a spectrum of, at the start, entirely blue, and then as we get further in duration, we should eventually get a whiter color being rendered on our surfaces, or as our trails. So if we now click play, select our surface, then we can wait, and we should see a kind of white set or a light blue set, and then we should see a blue set. So we can see that. It's a bit hard to tell there, but we have a light blue and a darker blue set being drawn out on our surface. And actually, if we undid that and increase our duration here, we could make this 4, and then we should get 4 steps. So we should see more of a kind of gradient there of our curves being drawn out. Also, we're using duration, but technically we're actually ranging from 0 to 3. So it's actually duration minus 1. So if we wanted that full spectrum all the way to white, then we would need to put duration in parentheses, and we could then subtract 1 so that we can give a max of 3. So really that's 0 to 3, so 255 divided by 3. Now if we click play, select our surface, then we should see that wider range of colors being drawn into our trails. So we can see those trails drawn out there on our surface, ranging from white to blue. We can hide that. It's a little bit hard to see with this particular background color. If we make our background a little bit darker, it's maybe a little bit easier to see there. So that is the simulated rainfall across our surface. We could even use this algorithm to, kind of make actual calculations or measurements based on random rainfall and the accumulation of particles. So we can make assumptions based on the properties of water or some liquid that's flowing across the surface, edit the mesh via erosion, or edit or kind of understand the amount of water or amount of fluid that might be collected in this particular surface. That's all for this video on gradient descent, but as I mentioned, there's a wide range of applications, and it's an incredibly powerful tool, so I highly recommend exploring some different use cases for it, different surfaces you can run it on, different kind of input or starting conditions, but also different ways of using it as a kind of analytical tool. What applications might you be interested in using it for? How might you edit this algorithm? So maybe, kind of add a cohesion. We know that, as water moves across a surface, if water has previously been there, then the kind of next water droplets are more likely to flow into that same path, which might be a cohesion behavior, and we know that water operates through cohesion. So those types of things are things that you now have all the tools to build yourself. So I highly encourage you to go ahead and do that. In the next videos, we're actually going to be stepping outside of Rhino, still looking at Python programming, but inside of a remote computing interface called Google Colab's Jupyter Notebooks. These allow for us to access incredibly powerful machines via the browser, so we can run our code entirely remotely, and we'll take a look at how to use ChatGPT and Google Gemini to help us build more robust and more powerful programming. These videos are going to focus on image generation using generative AI methods, including ComfyUI, which is a separate web interface for diffusion models. If you're not familiar with diffusion-based models, I'll cover that in that video, but both of the next two videos are going to cover topics of image generation and image editing using Python programming outside of the Rhino environment. This is going to kind of round out our skill set so that it's not just focused on 3D programming within one particular environment, but it's focused on a much more robust and wide-ranging, much more exciting kind of full spectrum of 3D programming, both inside of Rhino, outside of Rhino, and maybe some suggestions on ways to connect them.